In this example, we're going to take a look at multi-part motion. And multi-part motion is that motion which has an acceleration which changes somewhere in the problem. In this case, we have a car which is driving at a constant speed, and then the car hits the brakes to slow down and hopefully avoid hitting a deer. So that's going to be two parts. Now, multi-part problems tend to be moderately difficult to difficult. And the only real reason for that is that you have to keep track of two separate objects at the same time. The most important thing you can do to help yourself be more successful with these is to keep careful track of your information, make sure you identify all of the information that's available, and to keep a watchful eye for relationships which exist between the two objects that aren't explicitly given to you. Let's begin this problem. Step number one, it's just going to have us draw our picture. And so what we have is the car, it's moving at a constant velocity for this first segment. And I'm going to label this as part one. And then the car is going to hit its brakes, and it's going to travel for some distance, and we're just going to label this part two. Now remember, when we draw our diagram, that we always want to be very particular about labeling what's going on where in space. So we're going to say this is V initial of part one, which is equal to 24.6 meters per second. And at this point, we have V final of part one, which is also equal to V initial of part two, because it's the same point in space. And V final of part one, well, that's still 24.6 meters per second, because the car has not begun to slow down yet. Now, this entire time interval for part one is equal to 0.35 seconds. The time interval for part two is a completely unknown quantity. Let us just list out all the possible pieces of information that we could have for each part. And so basically we're just going to go through what is X initial, X final, V initial, V final, A, and T. So let's write all of those out. X initial is equal to 0. X final is unknown. V final, we already said, was the same as V initial. The acceleration is 0 because it's a constant speed, and we've already taken care of T. Now, in part 2, we have V initial, which we know is the same as V final from part 1, is 24.6 meters per second. Time is unknown. X initial is, for part 2, is an unknown quantity, but we do know that X initial of part 2 is going to be equal to X final of part 1. Then we have X final of part 2 is an unknown quantity. And I'm not going to put anything there yet. I need to talk to you about that in a second. Then we have V final of part 2. That's going to be 0 because the car is going to come to rest, presumably, hopefully, before it gets to the deer. And then the acceleration was given as 8.1 meters per second squared. So let's talk about the acceleration first. The acceleration, we're told, has a magnitude of 8.1, and it's a deceleration, which means it's slowing down. And part 1 is on the left, part 2 is on the right, and so that means the car is moving to the right. Therefore, the acceleration, since the car is slowing down, must have a direction which is opposite the velocity, and so that makes this a negative 8.1 meters per second squared. Now, X final of part 2. There's a couple of ways of looking at it, but really we're going to just say that X final is an unknown quantity that we're going to look for. I'm going to put this in as a box for the simple fact that the deer we know is located. If we say that x initial is right here for the whole problem, this is the origin, and we say that is 0. We know that this x is an unknown quantity. This x is also an unknown quantity. But the deer is at 52 meters, which means the deer is going to be here or somewhere over here, but we don't know where. So what we're going to do is find out where the car would end up if the deer wasn't anywhere to be seen. Just under these conditions, how far is that car going to move before it finally comes to rest? And then we'll compare this x final 2 with the location of the deer. Okay, so there are basically two approaches to solving this problem. I think one is going to be more of a natural approach for you, and then the other one is less natural, but should still be instinctive. One is dealing with positions and the other displacements. So basically what's going on is this. To go from here to here, we have a displacement in part 1, which we could just call d1. And then as we go from here to here, we have a displacement of part 2, which we could call d2. And so what are we ultimately looking for in this problem? Well, again, it comes back to your interpretation. Do you want to see it as displacements, or do you want to see it as positions? And we're going to do this both ways so you can see what I'm talking about. So I think the displacement one is going to be a bit more natural, because in order to know where the car stops, you would just say, oh, well, the total distance is displacement 1 plus displacement 2. And so this is one of those relationships that I was talking about. It's a fairly obvious one, and they're not all this obvious. But this was not given in the problem. You kind of have to see and understand physically what's going on. So what we could say is displacement total is equal to displacement 1 plus displacement 2. Now, when we solve problems, we try to break them down into bite-sized pieces, and we let the problem guide us, tell us what to do. The first thing we need to do is look at displacement 1. And for displacement 1, we need to find an equation which is going to describe the motion mathematically. We want to know how far we're going to go in this time interval. So because this is constant velocity, there's only one equation we're ever going to use, and that equation is d is equal to vt. And then we get to d2. Now we've got to select an equation for d2. The question is, which one is going to be the best one? Well, if you look at what we know and what we don't know, what we don't know is time. And since we don't have time, the most likely candidate as a starting point to find displacement 2 would be the time-independent equation of motion. That's going to be v final squared equals v initial squared plus 2ad. Now, v final in this particular problem is going to be 0, so this term goes away. And now we can rearrange it, and we get, because we're solving for d, we get minus v initial squared is equal to 2ad. So d is equal to minus v initial squared over 2a. So now we get d total is equal to d1, which was v1 times t1, plus d2, which is minus v initial squared over 2a. And so now all we have to do is substitute and solve. So d total is equal to v1, which is 24.6, times t1, which is 0.35, plus, all right, now this is where we have to be careful. This negative sign is not part of the square. So we're not going to square away that negative sign. So we have a negative times 24.6 quantity squared divided by 2 times a negative 8.1. Now, if you do all of your signs correctly, then you would expect this term right here, you would expect that term and that term to literally add up to give you a bigger number. If you mess up your minus sign, then you're going to see that D2 is going to subtract from D1, and D total is going to be somewhere to the left of your starting point, and that doesn't work. Now you're going to be tempted to just get rid of the negative sign somewhere and say that this must be the right answer, but that's not how you should do it. If you're doing things right, then the negative signs will always work out. Okay, so let's go ahead and calculate some of these values. All right, so we have 24.6 times 0.35. That's going to give us 8.61. So D total is equal to 8.61 plus. All right, now this negative cancels with that negative, so it all becomes positive. And now we get 24.6 quantity squared divided by 2 times 8.1. That's going to be 37.36. So we get 37.36. And so D total then is going to be that plus 8.61, which is 46.0. So our displacement was 46.0 meters. Part of your temptation is going to be to just say, oh, well, we end up over here at 46 meters. The deer was located over here at 52 meters, which is correct. And so X final here is 46. We don't collide with the deer, which is a really great thing. However, a displacement is not the same as position. And so for the sake of making it perfectly clear how this displacement becomes a position, we've got one more math step to do. By definition, D is equal to X final minus X initial. We know that X initial was up here. X initial was 0. So that term goes to 0, and the displacement does represent the final position. So I know it's a small point, but it's an important point. It's little details like that that you have to be careful with in physics. Okay, now the other way of solving this problem is to look at positions instead of displacements. And so instead of writing D's, we're going to write X's. And so the question is going to become, well, where do we start? Okay, well, I like to say that you always want to start at the obvious point, and that is part 2. That's going to be where the object ends up. Because what are we ultimately looking for in the problem? We're looking for this, right? We're looking for X final of part 2. So we need to model the motion of part 2, and then we'll fill in the blanks. And this is where we're going to really let the problem guide us. It's going to be a little bit strange to see it this way, but you'll get used to it as we go along. Okay, so for part 2, we've got 4 equations of motion to pick, but again, just like our reasoning over here, we said for D2 that we're going to use the time-independent equation because we don't know time, so we'll do the same thing here. So we get V final squared is equal to V initial squared plus 2AD. Actually, we should write that as 2A delta X because we're dealing with positions. And V final of part 2 we know is 0. And so we can rearrange this so that we get minus V initial squared over 2A is equal to delta X. Now remember that delta is final minus initial, so we can write this as X final minus X initial. So we get minus V initial squared over 2A is equal to X final minus X initial. And this is all for part 2, so let's put these subscripts in now before we get lost. X initial 2, X final 2, A2, and V initial 2. So we're going to move X initial 2 to the other side. It is a non-zero number, and so we get X final 2 is equal to X initial 2 minus V initial 2 squared over 2A for part 2. Okay, so let's go through our checklist. X initial 2, do we know it? Nope, sure don't. V initial 2, do we know it? Absolutely. A2, do we know it? Absolutely. So what we have to do now is we need to find X initial 2. And we're going to do that by using the equation for uniform motion. Because it's uniform motion, it's not accelerated. And so we'll do this. Just over here, just showing our work, we know that d is equal to vt, but d is really x final minus x initial is equal to vt. All of these quantities here relate to the first part of our motion, d1, right? So we could say that this is a d1, this is a v1, that's a t1. X initial of part 1 is 0, so we get x final of part 1 is equal to v1 times t. So t1. So we'll substitute v1 t1 in for x initial 2. That should be down there, not there. Okay, so we get x final 2 is equal to v1 t1 minus v initial 2 squared divided by 2a2. We'll substitute our values. So we have x final 2 is equal to, and v1 was 24.6 times 0.35 seconds, which of course is 8.61. The acceleration here is negative, and that's going to cancel with this negative, so we know it'll be positive. And so we get, let's see here, v initial 2 was 24.6. We'll square that, and we'll divide that by 2 times 8.1. And that gives us 37.36. And when we add that up, we have the exact same thing. That becomes 46.0 meters. So we get the exact same answer both ways. All right, so I know this was just a subtle difference, but the difference between using displacement and using position can make all the difference in the world whenever you're dealing with two object problems and two part motion problems. Because you lock yourself into locations in space instead of this displacement plus that displacement. Oh, I need to subtract a little bit here. Let the math take care of that for you. Okay, let's go ahead and take a look at the second part of the question. And we're asked to find the distance between the car and the deer once the car has come to a stop. So if we go back to our original drawing, we had the two-part motion. We had this initial part we called part 1, and that is the reaction time to take your foot from the gas pedal to the brake pedal. And then we had the stopping distance here. We called this part 2. And then this put us at 46 meters from the starting point of the problem. And we know that the deer was located out here at 52 meters. So we're being asked, what is that distance in there? So what is that delta x? And so that delta x is just going to be 52 minus 46, which is 6 meters. So there's about 18, 19 feet between the car and the deer when they finally come to rest. Okay, so we have a position time graph, a velocity time graph, and then finally the acceleration time graph. Take a moment and try to sketch this one on your own. Okay, so let's identify our key information. We have two-part motion. Part 1 is going to last for 0.35 seconds, starting from time t equals 0. We end at time t equals 0.35. We know that the velocity is constant, and that is equal to 24.6 meters per second, and that the displacement for part 1 is 8.61 meters. In part 2 of the motion, we don't know what the time interval is, but we're going to have to find it if we're going to plot it on this graph. The velocity initial is the 24.6 meters per second. The velocity final is going to be equal to 0. The acceleration was minus 8.1 meters per second squared. And the displacement of part 2 was equal to 37.4 meters. The first thing we want to do is, knowing we're going to need this time for part 2, let's go ahead and calculate the time interval there for part 2. And that's a simple task. We have the initial velocity, final velocity, and the acceleration. And so we can just use our velocity function, which is v final equals v initial plus at. We know that v final is 0. And so we get minus v initial divided by a is equal to t, or t2 more specifically. So t2 is going to be a negative 24.6 divided by a negative 8.1. And that is going to be 3.04 seconds. So T2 is equal to 3.04 seconds. All right, now notice that there's a negative sign out in front of V initial. That's part of the algebra, and it was essential in order to get the time as a positive value, because the acceleration implicitly is negative. That's what we have down here. And so the algebra always works out correctly with the signs. Unfortunately, negative signs are probably the most confusing part of doing physics, but it's something that with practice you can get good with. Okay, so we need to now set up our graphs, and I'm not going to take the time at the moment to properly scale everything out exactly correct. I'm just going to get you the shape of the graph that you should have. And our first time interval is very short. It is 0.35 seconds. And we'll just say that this part of our graph right here is going to be the end of our first time interval. And so that's going to be the same on all of these graphs. And then the end of our second time interval, I'm going to just put that out here. It probably should be further away, but for sake of simplicity, I'm going to leave it there because these axes should really be stretched out a little bit more, and you'll see why in a minute. Okay, so we have a constant velocity of 24.6 meters per second, and this is a positive velocity because we had the car moving to the right. So we should have a straight line which has a slope of 24.6 meters per second on the position time graph, and our final position should be at 8.61 meters. So we'll make that this point right here, and that means we're going to have a straight line that goes from here to here. Okay, now what does that look like on the velocity time graph? Well, on the velocity time graph, it's a constant velocity, and constant velocities are horizontal lines. And so if we just choose this as our, actually let's go up one more. If we choose this up here as our maximum velocity, that 24.6, then it's just going to be a horizontal line during this time interval. And on the acceleration time graph, we're just going to be down here on the x-axis where it's 0, because, make this really bold so that you can see it, but it's going to be 0 because there's no acceleration, so it's actually on the axis. Okay, for the second part of the motion, we have an acceleration of minus 8.1 meters per second squared. So I'll just label this down here as minus 8.1. And we're going to start here, and we're going to end here. And because it's a constant acceleration, it's going to be a horizontal line that connects these 2 points. And you can do a little dotted line up to the first point, and that would be all there. Now, quick check of your understanding. What does this area here represent? The area is equal to the change in velocity. It doesn't give you the initial velocity or final velocity, but only the change. So if the area there was equal to, well, the area there should be equal to 24.6 meters per second, what it doesn't tell you is, did you go from 24.6 to 0, or maybe 0 to minus 24.6? Okay, so we don't know. All we know is that that's how much the velocity changed by. Okay, so let's look at the velocity graph for this interval. And for this interval, we have a constant deceleration. And so we're going to go from our maximum to 0 during that time interval. So we're going to cross the axis here, come down to the axis there, and it's going to be a straight line. And then lastly, our position graph. This is the one that's going to be most confusing. The scale here is obviously not correct. We need a longer y-axis. So I'll take it up to here, and we'll just say at this point, all the way up here, that we are at 52 meters. Or I'm sorry, 46 meters is what we had for the motion. So we'll say it's 46 meters all the way up here, but clearly that's not properly scaled out. And that means we need to make our line stop here. Now, this is what we know about the motion. At this point in time, the car is stopped. Now, 0 velocity on a position time graph is going to look like a horizontal line. But we're not sitting at rest for any period of time. So it's only going to be one point where the velocity is, or where the slope is 0, because that's where the problem ends at that very instant. So we go from 24.6 to 0, and the slope of the position time graph gives us the velocity. So it's a positive velocity, but it's decreasing. So that means we're going to go from a slope which looks something like this to a slope which looks something like that to a slope which looks something like that. It's going to be decreasing with time. Now we know that acceleration on a position time graph is going to plot as a curved line, and it will be parabolic in shape. And so we're going to have to go from a steep line here to a horizontal line when we get to the top. So this is what our position time graph looks like. Now it's a good idea to, maybe label your graph, so that it's clear that this is a straight line, this time is noted, this is going to be a curved line, this is just an approximation.